Okay. So, yeah, sure. So can you hear me well? I guess so. Okay, I think we can start. So, welcome everyone. My name is Tomáš Smetana. I work for Red Hat. I work in the server experience team, more specifically in the systems management group. We've been working on a project named OpenLMI, which is one thing I'll be talking about today, and I'll be also talking about the Linux system management in general, about the problems of systems management. I would like to apologize because I don't feel quite well today, so it's going to be quite difficult for me to speak, and perhaps if you don't understand something I say, just ask me and I'll repeat it. So what's OpenLMI? OpenLMI is a project which goal was to provide a platform or some framework for Linux systems management. Basically, it's a set of APIs, remote APIs, and tools to use them remotely. This should allow sysadmins to configure and monitor the remote systems without need to log on them, because the usual way of managing systems today is to SSH on the remote system, change a config file, restart a service, or something like this. We have things like Ansible, which is just, SSH covered in other language, but it's SSH below. We have things like Puppet, which is not actually system management, it's just configuration management. It doesn't let you monitor anything. You cannot really explore or examine the state of the remote system. You only can tell it to, I want it to be in this state, so put it in this state, and that's the system management of Puppet and Ansible. OpenLMI is trying to be more interactive. You can take a look at particular property of the system, eventually change it, or just do whatever you want with that. We are trying to play nice with the others. So we chose to use standards for system management. In our case, it's standards from the DMTF, Distributed Management Task Force. It's a standards body consisting of all the big players in the industry. There's IBM, there's Microsoft, there's Cisco, Red Hat, of course. And these companies agree on something and build or write many standards for various domains, including computer management or systems management. The set of standards that's concerned with server management is named Web-Based Enterprise Management. That's the abbreviation, pronounced WebM. And part of the WebM standard is also CIM, Common Information Model. A Common Information Model is the core part of the standard in many ways, because it basically defines how to model the remote system. So it defines a set of classes that are pardon, a set of classes with properties, methods, also their interconnections, so their associations. It defines also how to interact with these classes. So that's why we chose this standard. It's actually quite prevalent outside of Linux world. Microsoft Windows has their own implementation of CIM. They call it WMI, and it's omnipresent in Windows. If you take a look at Windows machine today, you have PowerShell, and through PowerShell you can configure many aspects of the system. There's DCOM object model, thinly wrapped with WMI, which is the CIM, and through this you can do whatever you want. You can configure even Microsoft Office, I think, with WMI. You can configure IIS web server with WMI. You can do it remotely. You can do it from the PowerShell. That means well, kind of object-oriented language, but Microsoft way. And this is something that we basically lack on Linux these days. If you want to do something on Linux, you have to log on the remote system, figure out what this particular configuration file is in which format, and change it, hope it will work. So we wanted to use this standard because Microsoft Windows admins are used to it, and we were hoping that this might eventually make the adoption easier for them. OpenLMI is also trying to be modular. That means it's extendable. Any service, any subsystem, anyone who wants to create their manageability layer for their product can do so by creating parts that would work well with OpenLMI. And something that's not in the standards, but something that emerged as a necessity when we started to work with SIM in Linux was the client side, the tools. So we've developed also some scripting interfaces based on Python, and this is also the major focus of OpenLMI. We are not building GUIs. We are really just extending the existing, or the most common existing way of configuring Linux systems. Because today, if you want to manage large deployments, you usually use command line. The GUIs are not so popular and not so scalable these days. So we focus on command line interfaces. So what's the components we rely upon? Is the common information model. Common information model I've already mentioned. It's part of the WebM standards, and what I haven't mentioned is that it's huge. If you take the standards that, or the standard profiles that should, model the managed system, managed box, managed server, you'll get really a huge number of classes with a huge number of properties, with many methods, many interconnections, and it's very difficult to approach. The reason for it is, first, because the servers are really that complex. If you take storage with the file systems, with volume management, with RAID, with, network management, network storage, then this area is already complex enough. If you try to abstract from it, which is what SIM does, then you get even more complex system. Now add to this networking, add to this, memory, with distributed memories like NUMAs, then you get really, really complex system. So SIM itself is not really that easy to approach, and using it directly for the system management might be rather challenging, especially if you see it for the first time. The other component we rely on is SIM Object Manager. It's something that lets you access the SIM objects of the remote server. SIM Object Manager is basically a server that's running on the managed machine. Every managed machine has to have SIMOM. And there's more of them. On Linux, we usually have OpenPegasus. That's the one we use for OpenLMI. The other popular one is small footprint SIM broker, SFCB. It's created under I think it was by IBM originally. But we use OpenPegasus. We're also part of OpenPegasus upstream. And SIMOM itself only implements some basic classes for managing SIMOM itself and giving some basic data about the managed system. The important part of this concept is providers. Providers are basically plugins for the SIMOM. So we have plugin for networking, we have plugin for storage, we have plugin for user management, we have plugin for power management. There's more of them. I'll talk about them later. These plugins register themselves within the SIMOM and basically tell it, I implement these classes have these methods, and then the SIMOM knows how to route the requests eventually. And on the client side, I've already mentioned, we have the OpenLMI shell. OpenLMI shell is basically a Python command line, which automatically includes some modules for you to make it easy to work with the remote objects. If you start an LMI shell on the client, connect to the remote machine, then you can work with the remote objects as if they were local Python objects. This is quite convenient, and we found out that this is like probably the best client we found so far on Linux for SIM. Since I've already mentioned, SIM object model itself is rather complex, or the schemas are rather complex. We've tried to create something that would make the management really easy if you don't want to deal with the gore details of the model itself. So if you want to do a simple task, it should be simple. That's why we've created something named LMI meta command. You can imagine it as something like virsh for libvirt. You got a command with that lets you, I don't know, install package on the remote machine with, I don't know, few easy commands. It's also extensible, so you can add your own modules to the LMI meta command, and it can also serve as some example or boilerplate for custom scripts. So it should make it easier for anyone to start with SIM or with OpenLMI. So this is how it looks like when it's on a picture. So managed system is running SIMOM. SIMOM talks to providers and asks them to perform the actual tasks. So the providers themselves really change something on the system. Yes, even the interface between SIMOM and providers is standardized. So if you decide to change the SIMOM for, I don't know, you don't like our Pegasus, then you should be able to use the SFCB, and things should just work. Also, you can install other providers like Microsoft. Also, I think, offers a quite large set of providers for Linux systems, for monitoring, basically. SIMOM itself talks over network using HTTPS, wraps the SIM objects in, or encodes the SIM objects in XML. The authentication is also HTTP based, so it's basic HTTP by standard. And on the client, there could be just anything. Since the standard is quite old, I think it's been developed since early 1990s, if I'm correct. There's many language bindings for whatever language you like, so Java, Python, C, C++, Ruby, Perl, and so on. And on top of it, you can use either the standard tools we provide, or you can create your own using the bindings. So there's nothing fancy. I think this is quite this is quite common architecture for systems management on Linux. I think there's more products that use this. Agents, server, and then there's a client. I think it's broken. I'll tell you later. This is example of a object. I don't think you can read everything, especially those in the back part of the room. But this is how operating system is represented in a SIM. So you have class named operating system with properties like version, I don't know, number of users, maximum number of users. There's even methods, reboot, shutdown. And this also exhibits some other aspects of the SIM model. You can see that there are so-called associations. This is like relations between classes. So there's association boot OS from FS to file system. So we know which file system this operating system has been booted from. Then there's computer system. Association is named running OS. So we know this system is running on this machine. And there's aggregation, another type of sim class, and in this case it's named installed OS, so it represents all the installed operating systems on the computer system. Another interesting type of class is called the indication. Indication basically represents an event in the system. So we have concept of asynchronous events. These are extremely useful for things like alerts. If something wrong happens on the remote system, you can basically get to know without polling it. So this is how sim looks like, and you can see that even this is very simple. This is very simple class. Eventually, if you would take a look at things like storage, it probably wouldn't fit on screen of this size. Some constraints within which we try to operate. We decided that we will build only on top of system APIs, and we will not try to make mistakes of some other management software in the past. So we really use APIs wherever they are, and if they are not, we just decide not to manage that. I'm mentioning LinuxConf. I don't know who remembers LinuxConf. It's been a tool that, I don't know, it's 1998 or something. It was GTK UI that let you configure everything on the system, and it done it by editing the config files, which worked well until the user has decided to edit them manually too. Then it explodes, and it was like unrepairable. So we don't do that. And why is this important? And this is important because it actually shows where Linux is lacking behind its competition these days. We don't have APIs for complete system management ready at all. So I decided to show also practical examples. I promised practical examples, and there's going to be like most of the time. First of them is gathering some information about the remote system. So, okay, I forgot to start the VM. So the setup is like this. I will have this laptop as the client. There's virtual machine running inside. That's going to be my managed system, and I will use this as a console to remotely manage the virtual machine. So I'll wait when it gets lit. Good. Looks to be up. So how do I start? So the simplest thing, if you want to start with OpenLMI, is the LMI meta command. It's called LMI just, and wow. And good. See, when I type LMI help, it gave me the available commands. So you can see I have network, some services, storage, software, system. So let's see what system does. It looks like the thing I want. Okay, LMI system. So I don't know if you noticed, but the switch is -H to specify the host. So the host name is F22, and I'll do the system. So now it basically remotely connected to the virtual machine and gathered some data about it through SIM. So you can see that there's 3 network interfaces, that there is SA Linux turned off, that, oh no, it's in permissive, sorry, firewall is off, and that sorry, yeah, I have 2 CPUs, 2 gigabytes of memory. So this is basic information about the remote system. It can be used for, I don't know, some kind of inventarization. To show you what's happening behind, I'll use the LMI shell that exposes the object model itself. So you would see how it looks like. First, I'll connect to the system. Good. I have a connection. What I did now is I pressed tab. So there's tab completion. For every action, there is tab completion. So I have the object representing the connection. The connection now let me access the namespace where the same objects live. The root of the namespaces is called root, and you can see I have more of them. And there is, for example, method print namespaces for a namespace. So I'll do print namespaces. These are the namespaces which I have on my machine. The interop and PG, they are internal to the SIMM. DSIM is, I have no idea what. And SIMV2 is actually the one we're interested in, so I'll try to remember it. And now, if I do tab, you'll see this. This is the classes available on the remote system. Okay, it filled the buffer. So I know that there's more than 2,000 of them, and obviously this is not really something that easy to approach. So without documentation, I think you lost in the beginning, at least. However, I promise to show you what did the system information provider did below. So I know that, for example, the CPU. CPU has been represented by a class named LMI underscore processor. So how is here? For every class, there is a method named doc, which prints you the documentation of the class. So you are not that completely lost. But the documentation is very extensive, very verbose. However, you have some way how to explore the remote system. So now I have, I don't know. Since this is, again, this is Python. So I know I've seen that there's 2 processors, so I will iterate over that. What do I do? Okay. So what did I do? I don't know if you've, hopefully did. So I just iterated over the instances of class LMI processor. There's 2 of them. I didn't do any separation, so you have all the, and I printed all the properties of those classes. So you can see that it gave me the architecture of the processor, for example, clock speed. There's even flags. They're numbered, so we don't have the pretty print as you get from CPU info. And again, there's two of them, so here starts the second processor. You have seen that there's more information that I get from the system, and that's how SIM model works. Basically, the information is usually scattered over several classes or several instances of the classes. So for example, if I would like to get number of cores or number of threads, then I will have to find out the association that's named processor capabilities. Each LMI processor class has LMI processor capabilities association, and this processor capabilities association only contains the information about threads and cores. So I'll show you again the capabilities. Okay. I'll use the second processor because it's again, probably should explain what I've typed. So there's a method named associators which can give you a list of all the associations for a particular class. What I did is I filtered through them. So I only am interested in result in class that's LMI processor capabilities of all the LMI processor associations. And since there's more of them, it would be an array. I just chose the first one. I think there will be just one in this case. I'm not sure. So I have the new object. It's the capabilities of the processor, and I'll print its properties. So here I can finally find out that it has one core with one thread, and yeah. So that's how the SIM models represent, for example, processor. I'm not sure if you find it simple or not, but this is what the standard mandates. I think we've implemented we've implemented one of the DMTF profiles for physical machine. So we have it scattered like this in the objects. Okay. So that was the basic information about the hardware. Most of it is implemented in the hardware provider, but the system information I showed you is also taken also from the base classes implemented by the SIMOM. This provider is basically a read-only. It can't do any changes on the machine because, well, for obvious reasons. And again, another area show you is service management. Service management is quite easy these days on Linux, thanks to systemd. I know systemd is not universally popular, but for our needs, it actually brought quite many useful capabilities. For example, it has dbus API. Dbus API is something that we would eventually like to have with every service or with every aspect of the system. So service management can do all the usual things you would probably expect from it on the machine. So just quickly, yeah. Again, I will iterate over the services. So these are the services I have installed on the remote machine. I can try to get some particular ones. So I have prepared SmartD because it's safe. So SmartD would be again, I can use the tab completion to see the methods. And as you can see, there are things like start service, stop service, I don't know, restart service. So I can, for example, try to first print the properties. It's the safe thing to do. So you can see the status is OK. In our case, it means SmartD is up and running. I can do stop service. Looks like nothing wrong happened because I got 0 as reason value. Now I have to refresh the local object. The reason for this is because, wow, I'm slow. The reason for this is because we're really dealing with network, so it can be really slow. And if you do this from a script, you don't want to wait after each operation for your local objects to refresh. So we have it specified like explicitly. So if I do, again, print the properties, then you can see the status has changed to stopped. And eventually, if you take a look at the remote machine, it would be stopped. Storage, well, this is the biggest one of all. Storage is a huge topic on Linux because we have really various types of storage services and storage technologies we encapsulate. In OpenLMI, we've decided to build the storage provider on Blivet. Blivet is Anaconda's library for managing storage. The reason we chose chose Blivet was because it was the most complete API for storage we knew about, and it's probably the most complete API up to date, unfortunately, because we would like to have something like, I don't know, network manager for storage, but it doesn't exist yet. Hopefully, it's going to change. We're working on changing it, but it's really slow. I was about to show you some more about the how storage works, but I'm not sure if it's like that interesting because we, again, mostly typing the comments, and it looks very similar to what you saw already, which is the storage. Networking. Again, networking is based on Network Manager, and this is much better situation than in storage. Network Manager these days has already gained many of the enterprise capabilities, so it's able to configure not just the basic networking stuff like IP addresses and routing or DNS. It also can configure VLANs, bridging, bonding, teaming, I think data center bridging even. And the Network Manager guys really listen to their users, so Network Manager is really slowly evolving into a Swiss knife for networking. These days, I wouldn't mind running Network Manager on server. Our provider implements Smash DMTF model. That is, again, one of the DMTF standards. It has some specialities. For example, the configuration is separated from a state. So when you configure the NIC, the IP address or the card, you basically first create the configuration and then apply the configuration. This adds some extra steps, but adds some universality to this approach. Package management, again, we have now dbus API for managing packages. It's language agnostic. Actually, it's even package manager agnostic. PackageKit can work with RPM, can work with DPKG in Debian. So in theory, it should work on any distribution where it works. User management is based on libuser. This situation is not ideal. We are hoping to get some better API because libuser can safely work only with local accounts, if I'm correct. Eventually, SSSD will give us dbus API for configuring user databases wherever they're located, if it's in LDAP, if it's the local database, whatever. You can skip the demo. I don't have much time. Power management, it's built on uPower, and it allows for the basic power management tasks. So you can shut down, reboot, suspend, hibernate the system through this. Again, skip the demo. There's many other providers, smaller ones, or those I don't understand that much. First of them is FAN, that's been for controlling system fans, RAMD for enrolling the system into Active Directory or Kerberos domain. It's PCP for monitoring, for based on PCP product. There's SE Linux for configuring SE Linux. There's SSSD for configuring the SSSD daemon itself, not for getting data from the SSSD. There's locales provider for configuring locales, journal for reading logs, and there's logical file that's for preparing mount points. So because storage can mount file systems, so we have logical file to prepare the mount points. Where are we going next? I've shown you a really tiny fraction of what OpenLMI can do, and to your surprise, we don't plan to do much more. There's several reasons for that. First, we would like to hear more feedback from the users. We don't have as much as we wanted. It's no secret. So we will wait for people to start using it and tell us whether this works or not and what we should eventually change. The other thing is that, as I mentioned, we built on local APIs, and I think we are slowly getting short of them. I think we use all the APIs we've had, and now it's quite difficult to move further without doing some dirty hacks, which we don't want to do. So, for example, storage, there's big work ahead to create network manager for storage, for example. Services are basically not configurable these days. One of the first questions I've ever got from audience when talking about OpenLMI was, can I configure Apache with this? No, and the answer is still the same. No, you can't, because Apache doesn't provide API. Eventually, in the future, there would be more services. There are some. We know that it's possible. That would offer API for persistent configuration. Firewall can do it. Systemd can do it. I don't see a reason for Apache not to do it eventually in the future. Yes, it's bigger. So that's one reason we are not continuing. OK, I'm out of time. So there's future possibilities. I'll try to finish as fast as possible. There's other initiatives in system management. There's many of them. And in my opinion, we should try to make the system management invisible on the managed system. It should just be feature of the system is manageability. If it's not there, it's not manageable. We cannot build something on top of it and just try to maintain something on top of moving sand below. Cockpit project basically does it quite well. They expose local dbus APIs through some simple protocol and consume it in browser through JavaScript. So there's nothing running on the managed system, and there's nothing running on, well, almost nothing running on your managing system. You have pretty GUI. You can configure very many aspects of the remote system, but there's like no overhead, almost no overhead. So that's why I mentioned local APIs remoting. Now we have dbus, which looks to be like first sane IPC we have on Linux, and remoting is in in my opinion, one of the good ways ahead. And again, people have to realize, without API, there will be no configuration. No remote configuration is possible if you don't have local API and if you can't remote it. There's no monitoring without events. Again, something that should be obvious, but is not always. We have to know if RAID degrades, I want to get even from the system. I don't want to poll for it. I don't want to watch the system with fallen apart disk array. And yeah, we have to figure out how to do containers management and monitoring properly. So that's it. Timing was not ideal, so sorry for that. Here's the useful links for OpenLMI sites, and you can complain about my performance using the last one. So are there any questions eventually? There's no time for questions, I've been told. So if you have questions, I'll be lingering around for a few minutes. Thanks for listening. I'm really sorry, really sorry. Yeah, okay. It was so full, I haven't had the timing. I don't write.
Yeah,
I've never tried it in complete.
I'll have to go over. All right, I'll see you probably Monday.
Hopefully, yes.
I hope so.
Yeah, I'm sorry. It was terrible.